the derivative function. So up until this point in the course, we've been laying the foundation so we could finally reach the point where we talk about the derivative function. So again, the derivative is going to be the function that will allow us to get the instantaneous rate of change at any point for a given function. This is really powerful because again, if we know how a function is changing at a point, we know a bit about what the function's doing, how it's behaving, how we think it'll behave in the future, and we can use it to predict future values. Now, there's a couple ways to study the derivative function. The first is the algebraic and mathematical definition of derivatives. Before we get into that, I want to remind you that when we talked about continuity, we talked about how polynomials are continuous wherever they are defined. And we talked about what that meant. It meant that the limit was equal to the functional value. That's how we defined continuity. So that's really helpful for us because that means if we're taking limits and we're looking at a polynomial term, so polynomials are things like x, x squareds, x cubes, or whatever variable you're going to be using, that if the function itself is continuous, then we can plug the value in. Because it's continuous, it will be equal to the limit so that we don't have to do all the tedious calculations of small numbers. So let's start with the algebraic definition of the derivative function. So the definition of derivative says that for any function f, we define the derivative function f prime of x by the limit as h goes to 0 of f of x plus h minus f of x over h. Provided that the limit exists, the function is said to be differentiable at any point x at which the derivative function is defined. So that means if we have a function and we want to get the derivative function, which again will be the function that'll tell us the instantaneous rate of change at any point, we can use this limit to calculate it. I hope that the top of this limit looks familiar. If you think back to our composite functions, we were doing a lot of things like f of x plus h within our composite function section, which we'll now be able to apply here. Why does this definition make sense? Let's take a quick sidebar and look at a picture so we can understand why this limit will give us the definition of derivative. So remember, to get the derivative, we were using what we knew about the average rate of change to help us find the instantaneous rate of change. So we began by calculating f of b minus f of a over b minus a. Now, a and b were generic things that we chose to represent the endpoints. We don't have to use a and b. We could use c and d. We could have used f and z, right? These are just letters to represent two endpoints. So we could call one of them x and the other one x plus h. So what it is it's the x value plus some amount, meaning that it's to the right. Now, if we were to set up the average rate of change using x and x plus h, we would have f of x plus h minus f of x all divided by x plus h minus x, right? So f of b minus f of a over b minus a. Notice what happens on the bottom. We have an x and we have a minus x. So that simplifies into f of x plus h minus f of x divided by h. So the average rate of change between these 2 points is f of x plus h minus f of x all divided by h. That's equivalent to f of b minus f of a over b minus a. Where the limit comes in is this idea that the closer we get to the point we're interested in, right? We want to get smaller and smaller intervals by moving this point closer and closer. Now, before, we were just picking brand new values, but the equivalent statement here is letting h get really, really small. Because if h gets really small, that means that this point is moving closer to the point where we're trying to approximate. And the way we represent something getting really small is by introducing a limit. So we say the limit as h goes to 0, so that means that our average rates of change are getting closer and closer to x, gives us the derivative at that point, or the instantaneous rate of change. So let's start with an example and see how we can use this definition to find the derivative function. Example 1. Use the definition of derivative to find f prime of x if f of x equals x squared. So again, we're thinking about the function x squared, and we're trying to find a function that will tell us how quickly x squared is changing at any given point. So we go to our limit. So the definition says we're going to take the limit as h goes to 0 of f of x plus h. Now, let's do that as sort of a sidebar here so you can remember how we do that. F of x plus h means we're going to plug x plus h into our function. And our function was x squared, so that means f of x plus h is x plus h squared. Now here, we plug that in. We have x plus h squared minus f of x. So our f of x was x squared, all divided by h. Now, we want to start to do some of our algebraic simplification here. So what we're going to do is we're going to square out that top term to see if we can combine any like terms. So we get the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared, all divided by h. So here we have an x squared and we have a minus x squared. So those two terms will cancel, which leaves us with 2xh plus h squared divided by h. We can factor out an h term in the top here. So we have h times 2x plus h, all divided by h. Our h's will cancel, and we're left with the limit as h goes to 0 of 2x plus h. Now think about what kind of function h would be. If we just have h, that means it's a polynomial. It's raised to the first power. Since it's a polynomial, that means the limit as h goes to 0 is the same as if we were to plug in 0, because h itself is continuous. We couldn't do that before because it was in the denominator and it wouldn't be defined there. However, here it is. So we can let h go to 0, which means we're left with a 2x. That means that the derivative of this function is going to be 2x. So again, the derivative is a function. And what that function tells us is the instantaneous rate of change of x squared at any point. So if we want to know how quickly x squared is changing at 4, we could plug that into our derivative function and we would get 8. So the instantaneous rate of change of x squared at 4 would be 8. And we can plug that into the derivative instead of doing average rates of change around 4. So instead of using 3.99, 4, 4.01. So this is a more effective way to do it if we're able to solve it out. So let's take a look at another example of finding the derivative using the definition of derivative. Example 2. Use the definition of derivative to find f prime of 0 if f of x equals 2x squared minus 3x. So before, when we were approximating the instantaneous rate of change at 0, we would look a little bit to the left of 0 and take the average rate of change, and a little bit to the right of 0 to get the average rate of change to try to see what it was approaching. But now we want to use the definition of derivative. So remember, the definition of derivative looks like this. So when we plug in this definition into our function, the first term is f of x plus h. So f of x plus h is this first part right here. We're going to plug in an x plus h wherever we see an x, which is here and here. So we have two different terms. And then we have minus f of x. So we write minus, and then we put our parentheses around the function because that minus term has to go to both terms of f of x, all divided by h. Now we need to start our algebraic simplification. So for the first step, I'm going to square out the x plus h in that first term. So if I square that out, I'm going to get x squared plus 2xh plus h squared. Remember, there's still the 2 out front. I haven't touched any of the other terms yet. Now, what we want to do is we want to distribute this 2 to every term, but we also want to distribute the 3 into the second set of parentheses. After distributing, we get this result down here. So the 2 went in to multiply every term in the first parenthesis, and the 3 went in to multiply every term in the second parenthesis. I want you to notice that the first parenthesis has a 2x squared, and the very last parenthesis had a minus 2x squared. So those two terms are going to cancel each other out. Similarly, we had a minus 3x from the first part of our term, and then we actually have a plus 3x over here. So notice that this was negative, but this minus is going to cancel it out. So these 3 x's also cancel each other out. So now that those things are canceled, we're left with the limit as h goes to 0 of 4xh plus 2h squared minus 3h. So the minus 3h came from this little term over here that we've just been carrying along, all divided by h. So just like before, what I notice is that I can factor an h out of my numerator. And if I factor an h out, it's going to make my algebra a little bit easier. So here, when I factor the h out, I'm left with a 4x plus 2h minus 3. And I have an h on the top and an h on the bottom. So those will cancel. So now I have the limit as h goes to 0 of 4x plus 2h minus 3. So again, 2h is a polynomial term. And now that my h is no longer in the denominator, I can let h go to 0 because polynomials are continuous. And so after all my algebraic work is done, I have 4x minus 3. So remember what we were calculating. We were calculating the derivative, and we can write the derivative as f prime of x. So f prime of x equals 4x minus 3. But originally, the problem asked me for the derivative at 0. So since my derivative function will tell me the instantaneous rate of change at any point, I'm going to plug a 0 into my derivative, which will give me 4 times 0 minus 3, which gives me, ultimately, negative 3. So f prime of 0 equals negative 3. So that's how we can use the definition to find things algebraically. However, as your functions get more complicated, the algebra also gets more complicated. So we're going to take another approach at looking at the derivative function. We're going to do some graphical analysis to try to understand how to approximate the derivative from a graph. This is going to become very powerful for us as a tool to start talking more about